I was actually here about 2 years ago, right before I moved from New York to Denver, where I am right now, and was honored to speak here about gas turbine technology. So we're here today to talk about the impacts of generating at elevation, and there's pros and cons to that versus at the load. And we're going to talk about some major themes, and I'm going to bring up Gerard, and he's going to talk about the actual modeling we did at an economic basis, and we're going to kind of call that phase one. So I thought I'd shamelessly share a picture of my son. He's 3 years old, and he's convinced he's going to be a cowboy, a construction worker, or a fireman. So I took this shot, and I was like, wow, that's the Wyoming state logo, so I thought you guys might appreciate that. That's the local grocery store. For a cent, you can ride it for 30 seconds. So why are we here? So Lloyd pulled the team together to talk about basically the impacts of generating at elevation. What are the pros and cons doing this in Wyoming versus at the load center in California? What are the economics of doing it? And Gerard will walk us through an LCOE, or a levelized cost electricity analysis. And then finally, what's the best configuration of the plant? Meaning, is it a simple cycle plant? Is it a recip engine, some combination? Is it a large combined cycle, highly efficient plant? And what's the size of the plant? And then really the underlying theme here for Wyoming is, I think this could be a huge boost to the Wyoming economy and bring its wealth of natural resources to others around the country. You're blessed here with a lot of wind, a lot of gas, and a lot of coal, and I think there's something to be had here. So real quick, 3 trends, and this is nothing new, but I thought we'd just kind of set the stage as to why this may make sense in the long term. So we'll talk about renewables impact, cheap natural gas, and then finally the impact of retirement coal plants. So nothing new, right? The age of gas is here. For the next 10 years, we're expecting gas to sit at about $4 to $6 a million BTU. Even $8 is historically relatively inexpensive. You can see on the left side there, North America, that's the unconventional gas story. We're about halfway through that ramp up in production capability, and at this point, there's no line of sight to that ending. Now, cheap oil could have an impact, kind of unclear on what that might do. LNG investment, that could be a two-edged sword, right? So some argue that LNG markets globally could drive price up. Others argue that it'll just increase supply and prices stay fairly constant. So here's the duck curve kind of split out, and this is actually a Germany example. I like this because it does split out the different aspects of the curve. So you look at the top blue line, that's the load that at this case Germany is experiencing. So you take the wind and solar, solar being in green at the bottom, and then wind being that middle green line, and you combine the two, and you've got what looks like, I'll call it the bottom half of the duck. You combine that with the blue and the red, and you've got the gray line, which is the duck curve we've all seen, and that's the challenge of ramping down and ramping up. So what better generation to support that than a gas turbine? Highly flexible, we can turn it down, and highly efficient. Another snapshot, called the heart attack chart. So that's kind of a daily view, same story. And then finally, coal retirement. So I would, the absolute numbers, I don't have a lot of faith in. I mean, they're going to change, period. But the reality is there is a trend of coal plants retiring. And with the EPA regulations of the pounds per CO2 of megawatt hour, it's going to be difficult to get a new coal plant put online without some new technology, which is coming. I would just say in the next 5 to 10 years, it's a tough cost challenge, and that's just the reality. So quickly, I'm going to go over this very quickly and then just kind of touch the high points. So what are the advantages? Lowest dollar per kilowatt. So as an example, in Texas right now, customers are putting in large 2x1 combined cycles at around $7.50 a kilowatt, which is incredibly low. And these are plants that are 61% efficient. So it's the most efficient use of fuel. Cleaner, it is on a CO2 basis about half the emissions of coal. Now that's not to say that coal is bad. This is just to say that to help states meet 111D requirements, gas could be part of that equation. A little bit of an eye chart, I'm not going to go through it, but the bottom line here is, if you look at the right-hand side, this is kind of a rack and stack of the LCOEs by technology. And you look at the two cheapest ones, wind and gas, great Wyoming resources. And honestly, look at coal. Coal is actually not that much more expensive. You look at the yellow line. So again, I think coal has a strong place in the U.S. economy. You look at the Northeast, the polar vortex last year, go talk to one of those ISOs and ask them how key a coal plant was, because think about it, gas was constrained, and the only plants that could run, because they got a 30-day supply, were the coal plants. So honestly, coal probably saved somewhat of a grid crash in the Northeast last year. So finally, what's the reason we can actually ask this question about generating at elevation? And the reality is these transmission lines that are going to get built, we hope, over time, actually make this an opportunity. So you think about it, if you had to build a dedicated line for a single power plant, it probably would be cost prohibitive. But if you could piggyback on this line that some folks in this room are working on, I think the economics actually become pretty compelling. So final slide before I bring Gerard up. So where you site a plant makes a huge difference. So I'm going to kind of outline the positive benefits of either putting it in California or Southern Nevada, and then the positive aspects of siting it in Wyoming with a wind project that is managed to develop a transmission line. So in California, you're close to the load, so that minimizes transmission constraints. A great example is the SCE RFP that came out last year. So they actually gave individual sites a locational effectiveness factor. So for example, a site that had a 1.2, whatever you bid in that RFP, they multiply by 1.2 because it was on a good site. Conversely, a bad site from a transmission perspective would have been given like a 0.8. Fewer line losses, so you have to account the fact that you're going to travel the better part of 800 miles, I think. So there's a 5% loss that California plants wouldn't experience. Less cost overall. And then finally, lower elevation, just gas turbine 101. Elevation's not good and temperature's not good. So these guys have the advantage of a lower elevation. Then go to Wyoming. Here we have an advantage of lower temperatures. So those kind of offset each other to some degree. The other huge advantage this site would have in Wyoming, labor costs and overall construction costs are less. So dollar per kilowatt, this particular location has an advantage. Well mouth, gas prices. So gas prices in Wyoming traditionally are lower. Gerard kind of coined the phrase well mouth. So in theory, you could have a gas well right next to the plant, much like mine mouth, and even use low-cost ethane. So there's projects in the U.S. that get ethane for, I think, $1 a million BTU. We can burn 25% of that in a gas plant. And then finally, I think one of the biggest reasons is it would promote new transmission projects. So a transmission project that has a 45% capacity wind project next to it is underutilized for that line, right? So a gas plant could pay a tariff, use that line on a more consistent basis. So what's the right answer? Let's bring up Gerard, and he'll talk us through some of the fundamental economics.
Okay, just a little introduction. My name is Gerard Loiselle. I forgive everybody on my last name because I grew up in Maine. It's French, but we've Americanized it. And then my mom, I got to blame my mom for Gerard. Everybody, Jared, Gerald, the federal government on my tax return calls me Gerald, so I get used to it. It's not a problem, thank you. No, actually, Ty spelled my name wrong on the first slide, so I get it from my coworkers too. So we're going to talk today how we just looked at a quick cost of energy. We looked at levelized cost of electricity, sometimes also called levelized cost of energy. This is the way vertically integrated utilities would look at a new plant 10, maybe 20 years ago. And you'll see, first of all, I want to point out the metric here, cents per kilowatt hour. Before I took this job about 6 years ago, more on the sales side, after about 15 years in engineering, I never looked at my electricity bill. It was a bill I got every month, and I had a lump sum number as $100, $150. But if you actually look in there, typically they will give you a cents per kilowatt hour number, as that's the price of the electricity that's being served. What goes into that number? 3 basic costs. Capital costs, you got to build the plant. Operational costs, these are the people running the plant, the upkeep of the plant over the life, and the fuel cost. The fuel cost isn't quite so simple. There's also an efficiency term in there. How efficiently are you converting that fuel into electricity? And that's going to be different for either a different fuel, coal or natural gas, or a different plant, simple cycle, which is a gas turbine only, or combined cycle. The levelization factor, why do we talk about levelized? It's a way to look at something over a certain term. For this analysis, we looked at 20 years, and then we looked at what things are changing over that term. Interest on the capital expense, and escalation of the fuel, people's salaries, and other stuff. So we can look at that over a 20-year period. What really you're trying to do is, this is the price at which electricity needs to be sold in order to cover all the costs. The 3 components of the cost, capital cost, sometimes called capital expense or CapEx, over a 20-year life is about 30% of the cost of the plant. Operation and maintenance about 10%, fuel cost is about 60%. Now that capital cost has a return on investment. Typically that used to be set by a Public Utility Commission. But as Ty mentioned, a couple of things. Capital costs, we believe, would be less expensive here in Wyoming, and fuel costs could be less expensive here in Wyoming. And that's 90% of the cost of the plant over 20 years. That's the only thing that would allow this to work. So looking at the various sites, we looked at 5 different sites and 5 different technologies. So the capital expense, higher in Nevada or California, lower in Wyoming. And we looked, it was about 20 to 30% different depending on the technology. The fuel, we said, was higher in Nevada, lower in Wyoming. It was about 50 cents different, so between $4 and $4.50 a gas. That would be escalated over the 20 years, and that delta would get larger over time. Ty mentioned the site temperature, so any gas turbine is going to have worse performance on a hot day, lower density of the air coming in. Site elevation, higher in Wyoming, less power for the same gas turbine. So the gas turbine costs you the same, can you produce less power? The way I explain pretty much everything to my family is about cars. They don't know what I do. So I say it's like driving your car up over a pass. You step on the gas, you don't have any more power. You simply can't get any more oxygen into the system. Same thing that's happening at elevation. However, offsetting some of this, line loss. You're having to transmit over large distances. We have accounted for that. It's about 5% from here into California. Financial assumption is the same. We're assuming that someone's willing to take the same rate of return on the plant. Prices for salaries and everything else are the same for Wyoming and California. And these were the sites. We did 3 in Wyoming, 1 in Colorado, and then Southern Nevada. Southern Nevada is a proxy for either Nevada or California. We looked at simple cycle heavy-duty gas turbine, simple cycle arrows, those are gas turbines made from aircraft engines, reciprocating engines, and then 2 combined cycle plants, 1 based on F-class technology and 1 based on H-class. The H-class is a little more advanced, a little more efficient. So the more expensive the gas, the longer you run, the better that more efficient plant is going to look. So, summary of the results. The top you're never going to read, but obviously we did a lot of calculations. Summary in the COE. So Platte County, for all 5 types of generation we looked at, was the least expensive. In addition, the combined cycle, the most efficient combined cycle, was pretty much the best for all the different sites, meaning the lowest cost of electricity was a combined cycle, the highest efficiency combined cycle, located in Platte County, Wyoming, with the line losses over time. So with the assumptions we put in, over 20 years, this could produce the lowest cost of electricity, or a lower cost of electricity, let's put it that way, than something being generated in California, even taking into account that it may be lower power output. So the last thing we want to look at, when you talk about natural gas generation, especially with gas turbines, we talk a lot about flexibility. The OEMs, the original equipment manufacturers like GE, have worked a lot on this in the last 5 years, and this is in response to stuff like the duck curve. How quickly can you start the plant? Well, simple cycle gas turbines can start in 10 minutes. Combined cycle plants now can produce power in 10 minutes and be at full load in about half an hour. Ramp rate, how quickly can you increase the power in the plant? And it's measured in megawatts per minute. These are things that either the market has to pay the generator for, or they have to get some value in some other way. Why does that play into Wyoming? Potentially, if we're talking about putting wind down the line to California, if this resource is on this side of the line, you can balance out what's going to California. Now, will someone in Wyoming get paid for this generation or get paid for this capability when California is that far away from CalISO? I'm inclined to think not, but the capabilities would be in there. Minimum turn down is important. We talked about negative power prices. So if you can turn down, stay online, and be available, you simply burn less money. So you lose less money overnight. So those are the things we've looked at on the capabilities of our gas turbines in response to what we've seen in the marketplace. And now I'm going to hand it back to Ty to wrap up.
Three conclusions we've reached is it does make sense, economically viable option, but I think the piece there that we got to understand more is what is the transmission impact in California? Do they want a single point DC line coming in with 3,000 megawatts? I think we can figure it out, but I think there's some additional work that needs to be done on the transmission side. I think the second bullet there is huge. I really believe economics for these large transmission lines can be improved if you've got a gas plant that is utilizing essentially that pipeline. And then finally, from a configuration perspective, no surprise, if you're going to run 4,000 hours or more a year, an efficient combined cycle is the right answer. And with today's very flexible, fast start gas turbines and flexible plants, I think you don't give up a lot of flexibility of a simple cycle gas turbine either. So 2 next steps, I think we need to run some sensitivities after we get feedback from, of course, this audience and others. Things like fuel price, costs that we've assumed, probably could use some refinement. And then finally, back to the grid. We've got groups inside G that do these studies. I'm sure there's other groups out there. But just understanding how the grid would deal with a block of power this big coming from 1,000 miles away.
Questions from the board?
Thanks, guys. I had a couple of questions, and maybe just for everybody else, we've been hearing more lately. Lloyd and I went to the NRECA conference down in Orlando. Can you talk and explain to people some of the things you've done for improving the ramp rate, the turn down on these type of systems without hurting service life and warranty life and things of that nature that you've done, that you commented over the last 5 years to accommodate this variable ramping new issue on the electric grid?
Yep, so that could be a 2-hour discussion in itself, but if you just take the basics of a gas turbine, we've designed these gas turbines such that starting it fast has no maintenance impact anymore. Things like compressor clearances, we've adjusted for such things. The efficiency really comes from firing temperatures. So the gas turbines fire hotter. We've got better materials, better coatings, so that's where the efficiency is coming from. And then the plant design is such that we've essentially separated the gas turbine and steam turbine. So the gas turbine starts as fast as it wants to, steam turbine catches up, and you're at base load in 30 minutes.
Okay.
Versus a plant, say, 10 years ago, that would take 2 hours.
Yeah, so that's a big improvement.
It's huge.
Over 10 years. So I just want to make sure. The other question I had, and that was kind of following up on what Rich Walgie talked about earlier today, and that is they're seeing if they're taking existing plants offline, like coal plants, that there's a grid instability problem that occurs, and then he has to, they're having to look at other investments on the order of $50 million, such as synchronous condensers. Are there opportunities with these types of generations to fill that or help obviate those problems when they start shutting down some of these coal plants?
I think there would be, and the reason I'm hesitating is because that's an AC issue. If this is a DC line, I think you have to look at the receiving end of it and see if there's hardware get to install in there. My gut reaction, and maybe Gerard has an opinion, is if you're going to site a gas plant and a wind plant at the same location at the far end of a DC line, I think much of that balancing happens at this end, and on the receiving end, there's less impact. And this is the grid aspect that I'm just not completely clear on yet, because it's a pretty complex question.
Question from the audience?
At the end of the
Hello.
At the end of the day, high levels of integration of wind and solar present some grid management problems and grid stability problems because of its intermittency. And the solution for that is storage. And the output of the storage vault, at least in the compressed air case, is a gas turbine. Have you modeled what the overall levelized cost of energy would be in a hybrid system like that?
We have not. I'm aware of a project out there that is looking at doing just this. It's in Utah. I'm going to say the LCOE on that project is going to be significantly more because you have more hardware. The benefit is if you compare that storage capability to, say, a battery or a flywheel, I think it'd be much less. So there's on an absolute basis, it will be higher, but it'll be probably one of the lower LCOEs for storage.
But the operating fuel costs go down because you're not using as much energy
Correct.
to compress the air. And your overall natural gas compressor cost goes down because you don't need as big one as you had, so you can move some of that capital investment
Right.
into the creation of the vault. And so the question is, have you ever tried to look at that as a holistic system?
We haven't, no.
I'd be interested in the numbers.
So we appreciate you guys, and I think you got some feedback from Don and I to your folks in Orlando. So we've had nothing but good things to say, even though I need to work on my French, Gerard. But
Like I said, it's Loiselle now, but originally I believe it was Loiselle. I don't say that way, so.
So anyway, Ty and Gerard have agreed to put together a report, and we'll get that. We'll put out a news release on that, distribute it to our 1,300 stakeholders on our listserv. So that'll be a good thing for GE and for Wyoming as well.
Thank you, Lloyd. Let's see, could co-production of electricity and petrochemicals be appropriate to this playing field?
Meaning the gas plant would support chemicals or other products at the same time?
Yeah, once you got your syngas, you could switch it. You could
Oh,
go to electricity.
absolutely, yeah.
Or some sort of petrochemical.
Correct, so yeah.
Yeah, so what we looked at was a natural gas combined cycle, and so it would be taking pretty much pipeline gas. So we don't have a gas fire on this. So in all this analysis. Now, the plant could be set up if natural gas were to be used for other products, it could be done, but that wasn't part of our analysis.
Well, let's give these gentlemen a hand. Thank you so much.